Okay, hello everyone. My name is Yinan. I'm going to talk about Apache Spark in Kubernetes. So basically, I'm going to give a technical deep dive into some of the internal of this project. For the rest of the presentation, I'm going to use English actually. Because for some of the terms, it's really hard to translate them into Chinese and back and forth. So I'm going to stick to English for the rest of the presentation. Okay, first I'm going to start off to talk about some of the motivation behind this project, and also I will give a brief overview of the history of the project. Following that, I will do a technical deep dive into some of the internals of how everything works together. Then we'll talk about some of the existing features that we have already made into Spark. And I will give an overview of some of the future roadmap, so what you can expect from the community. So what kind of new feature you will see in the upcoming Spark releases. Finally, I'll take some questions. Some background about myself. I'm a software engineer on the GKE workloads team at Google. I also co-chair the Kubernetes Big Data. I'm also an Apache Spark committer. Mainly due to my work to the Spark on Kubernetes integration. There's a lot of reasons why people want to run Spark natively on Kubernetes, but I think these are the main reasons behind the project. So one of the main reasons, the rapidly growing ecosystem around Docker container and Kubernetes. So people might have already been running a lot of these tooling for their online serving workloads or stateless workloads. So naturally, they want to run all these tooling, also for batch kind of workloads or data processing workloads. So they want to leverage these rich tooling also for their batch workloads. So another reason is there's actually an increasing trend of people adopting multi-cloud or hybrid cloud environments. So you might have you might use services from more than one cloud providers, and you might run some services on Google or some part of the services on, for example, Amazon. Also some companies actually they do hybrid setup. So they run part of their workloads on in the cloud. In the meanwhile, they also run some of their workloads on their on-prem data centers. So in that case, portability is the key. So you want to achieve portability by basically you don't need to do anything. Then you can move your workloads from one environment to the other. So Kubernetes is the key to achieve portability. So naturally, we want Spark to be able to natively run on Kubernetes. So last but not least, we see a trend people wanted to consolidate their hardware resources. So traditionally, people run big data workloads on things like Yarn or Mesos. We're seeing increasingly people wanted to move all these data processing workloads also to Kubernetes. Well, for the reason they're already operating Kubernetes cluster for their online serving workloads. So they don't want to maintain two operation team, one for Kubernetes, but then one for the other. So why not just combine them together? So they just need to operate one environment for all their workloads. So and also by combining different kind of hardware environments into one, you can achieve better resource utilization. You can reduce cost, all these kind of benefits. Some background about Spark, just in case you don't know that. So it's currently the most popular framework for large-scale data processing. It's often considered the next generation Hadoop. So it's actually widely used by some of the world's largest companies, like Tencent, Facebook, Uber, JD.com. So it has several language bindings. You can actually run Spark. You can write Spark in Python, in Scala, in Java, or in R. It also has a SQL interface, so you can actually run SQL queries on Spark natively. Sometimes Spark is called the unified analytics engine. Well, by that it means like you can actually run all kinds of different batch workloads and streaming workloads and sometimes machine learning workloads and graph processing workloads all on Spark. So you have one shop for all kinds of analytics needs. So currently on GitHub it has over 19,000 starts and over 17,000 forks. So together with Kubernetes, they are basically two of the most popular open source projects, on GitHub. So this is a sort of timeline of the project history. So in November 2016, we started the design, and soon after that, in December, we started the dev work on in a fork actually. So the reason why we chose to do it in a fork is so we wanted to be iterating really fast. So without doing all the code review stuff against the main repo. So we decided to do it in a fork. So in mid 2017, we poured all the work from Spark 2.1 to Spark 2.2, but it's still in a fork. And we did a beta release, and so people can actually get a sense on what that was really, and also gave us feedbacks on issues. So in September 2017, the SPIP, which stands for Spark Project Improvement Proposal, passed. So that means actually we could start porting the work we did in the fork to the main Spark repo. So around the time frame of December 2017 and January 2018, so part of the work that we did in the fork was upstreamed into Spark 2.3. So that's when the work was seen by the mainstream users. So basically, people started to talk about the Spark on Kubernetes since the release of Spark 2.3. So in October, well, basically, just about a month ago, so we added more feature into Spark 2.4 that I will talk about in the later part of the presentation. So on a high level, the native integration with Kubernetes in Apache Spark basically gives you another option to run your Spark jobs. So it sits besides standalone Yarn and Mesos. That means actually you can run. Now you have the fourth choices, so you can actually run Spark job natively on Kubernetes, like what you would run that on any other coarse-grained scheduler backends. So the native integration with Kubernetes in Spark basically has two parts. There's a Kubernetes-specific submission client, and also there's a Kubernetes scheduler backend that runs in the driver. So when it comes to the submission client, it's actually pretty straightforward. So it starts with a empty driver pod spec. And it applies a bunch of what we call feature steps to the empty driver's pod spec. And finally, it generates the final driver pod spec and then sends it to the API server to create the driver pod. So then the Kubernetes master or the scheduler basically schedules the driver pod to run on some of the node. So some of the feature steps does things like mounting volumes or mounting secrets, and also adding environment variables specified by the users, those kind of things. So basically, each feature step adds some part of customization into the driver pod spec. So the final result is a complete driver pod spec that you can just send to the API server for creating the driver pod. So the other part is the scheduler backend, which is a custom implementation of the coarse-grained scheduler backend in Spark. It runs in the driver. So the responsibility of the scheduler backend is basically it acts as a sort of like a custom controllers for executor pods. So it manages manages the life cycle of these executor pods. So together with the Spark core, it does these things so they handle task scheduling. So the scheduler backend manages the executor pods. So it also once the executor pod starts running, so the scheduler backend will watch the events on these pods and take actions on certain events. For example, if for whatever reason one of the executor pods is deleted from the cluster, so the schedule backend will try to recreate that. So the backend actually takes the Spark configuration from the Spark core, and also it takes order to request new executor or queue existing executors from the Spark core, and does the things accordingly by talking to the API server. So on a cluster side, so the Kubernetes cluster basically, so it provides these very basic services. It schedules and runs your driver and executor pods, and it provides networking support. So you can actually, so for example, if you want to talk to and remote HDFS cluster, or it also provides networking support for the executor pod to connect to the driver. And it also provides the logging support, so you can actually use KubeCon logs to fetch the logs of either your driver or your executor pods. So under the hood, so when someone like a user runs Spark Submit by giving it a master URL that starts with KDS. So what happens underneath is that. So the submission clients will run these steps that I just mentioned to create a driver pod spec, then send it to the API server. So once the driver pod gets created, the master will schedule that to run on some of the nodes in a cluster. So once the driver pod starts running, we'll request executor pods in mini batches. So they will try to start a batch of executor pods whenever that possible. So then the master will try to schedule these executor pods onto some of the nodes on the cluster. So once they start, they will connect to the driver pod to, so now your application, your Spark app is basically is running like it would normally. So, and in the meanwhile, so once the executor pods start running, so the driver pod will start watching the events, the pod events on these executor pods and take actions accordingly. So the way or the process the executor pods get created is very similar. So the driver pod takes an empty executor pod spec and then runs a bunch of steps on the empty executor pod spec to generate what do we call the final executor pod spec, and then send it to the API server. So this will basically create one executor pod. So again, these steps do things like if you want to mount some secrets to your executor pod. So for example, you want to access some remote services, or for example, HDFS, secure HDFS. The secret might carry the delegation token in it. So you want to actually mount that into your pods, so they can actually use that for remote access. So yeah, so then once the executor pod gets scheduled, it starts running, and we attach a empty dir volume to be used for as the working directory for the executor. So because of the way networking works in Kubernetes, so the way the executor pods connect to the driver pod is also pretty interesting. So on Yarn or on other scheduled backends, usually networking connectivity is granted. Like you would assume, so the executor pods will be able to talk to the driver pod natively. But on Kubernetes, things are different. So actually, the executor pods connect to the driver pods through a fully qualified DNS name. So on Kubernetes, in order to give a pod a fully qualified DNS name, you have to put the pod behind a service. So this is actually handled by the submission client. So the submission client, before creating a driver pod, it actually creates a headless service for the pod. So this basically gives the driver pod a fully qualified DNS name. So then, so after that, once the executor pod start, they can actually use this FQDN name to talk to the driver. So yeah, this animation basically shows what happens. So the driver, So the submission client basically sets up a service for the endpoint and driver for the driver and block manager in the driver process. So this is actually a headless service, which is pretty straightforward. And then after that, the executor will be able to connect to the driver using that service. So again, because of the way Kubernetes works, so something you naturally do in with other scheduler backends like Yarn or Mesos wouldn't work in Kubernetes. One thing is you can't, because the driver runs in the cluster in a pod, it doesn't have access to these application dependencies like jars or data or config files on your local submission machine. So to solve these problems, actually we support these kind of two dependency management options. One is, we basically provide a set of basic images you can use to build upon. So one way is, you can always bake your dependencies into your custom images. Then use these to run as the Spark driver or the executors, which basically already have all the dependencies locally within the container. Or the other way that we usually recommend for large amount of data is that you just put your data or large dependencies like jars onto some remote storage system like HDFS or Google Cloud Storage or Amazon S3. Then you basically access these remote storage just like you usually do. So you give them an HTTP endpoint or an HDFS URL. So Spark itself knows how to access these files. So there's also some difference in terms of so how remote application dependencies get handled by the driver between Spark 2.3 and Spark 2.4. So in Spark 2.3, we actually used an init container for downloading the remote dependencies in the driver. So what happens so the submission client will add an init container into the driver pod. So that init container will be responsible for downloading these application dependencies like jars or files onto a user-specified location. So once it successfully downloads all these things, it will add all the jars to the class path. So you can actually naturally you can access these jars in your Spark program. So in Spark 2.4, actually since the release of Spark 2.3, there are some debates over the use of init container because while the Spark community was not very happy with the use of this init container, which adds complexity, also some more code to maintain. So then we decided to get rid of the init container. So so the solution would be to actually run the driver container, so to run the Spark submit command in client mode in the driver container. So by doing that, we can actually leverage the native support in Spark itself for downloading application dependencies because Spark itself knows how to download dependencies before it starts running your program. So, but with that change, there's a very significant change. So files are no longer downloaded to a user-specified location, but rather these files get downloaded into the local working directory and enter a randomly generated directory. So you can still access things like jars naturally because these will be added to the class path. But if you have some file you want to access by a file path, so you have to use the Spark files.get to resolve these file paths, basically. So this basically gives the list of existing feature as of Spark 2.4. So we have, we have the basic submission client and the native scheduler backend in the repo. Well, so we also support these languages. So you can actually use Java, Scala, Python, or R. It also supports running SQL queries. For example, you can actually set up the SQL. I forgot actually what's it called, but there's actually some kind of a server you can actually run in Spark. Then you can send SQL queries to. So you can also do that. So currently, it only supports static resource allocation. That means actually you have to figure out how many executors you want, and so you can't change the number of executors at runtime. So it supports for both container local and remote dependencies, like what I just described. And it also supports these basic, pod customizations. For example, you can add, you can specify hard CPU and memory limits on the pods. So this is actually one thing, the Spark native, Kubernetes integration is different from the Yarn or Mesos integration is that you can actually use fractional values for CPUs for both driver and executors. For example, you can actually use like a 0.5 or 100 milli CPUs for your driver or executors, which you cannot do in other schedule backends. So you can also set these standard things like label annotations or environment variables for your pods. You can also mount arbitrary Kubernetes secrets into the pods. So it also has limited support of these basic volume types like empty-dir, host paths, or PVCs. So you can also use image pool secrets to pull images from some private image registries. So it also comes with full cluster mode support and also limited client mode support. By that, I will talk about that later, so what I mean by limited. In Spark 2.4, we added the client mode support. This is actually one of the most requested features since the release of the Spark 2.3. So with this, you can actually run interactive applications like notebooks, like Jupyter or Zeppelin notebooks, or Spark Shell programs with the native Kubernetes integration. So you can actually run the driver both outside or inside the cluster. But there's a tricky part when you run the driver outside the cluster, because users are responsible for setting up the network connectivity from your executor pod running in the cluster to the driver pod, to the driver running outside the cluster, so which is not always possible. So you have to take that into consideration. So the recommended way is, if you want to run, especially if you want to run notebook kind of applications, you want to run these things in the cluster. So that means actually you run your client in the cluster in a pod. For example, you actually run your Jupyter notebook in a pod. So then the networking connectivity part is much easier to handle. So what happens, so you can just create a header service manually. So this is, because it runs in the client mode, so the submission client won't be run at all. So at least the part of that handles the creation of the driver pod won't be run. So you won't, that means actually there won't be an entity that will create the service for you. So you have to do that manually. So usually the process, you create a service first, use some label selector that you will later apply to the driver pod. So then you start your driver pod. So then the service you create previously will be bound to the driver pod. So also, if you run your driver pod, if you run your driver in a client, in a cluster, you can also leverage garbage collection. So, for example, if you, for whatever reason, you delete your driver pod, so all the executor pods created by the driver pod will be gone due to garbage collection. So, so this is basically visualize how it works. So you create a headless service before you create your driver pod. The driver pod gets a DNS name from the service. So in Spark 3.0, which will come next, we also added support for Kerberos authentication. So you can actually use that for secure HDFS access. I know, most enterprises who run HDFS very likely will have authentication enabled for security purposes. This is also supported in Spark itself. So to use this feature, you have to give the schedule backend two things. One is the delegation token you use to access secure HDFS. The second is some header configuration that the driver knows how to talk to your HDFS name node for authentication. So when it comes to delegation token, actually there's two ways you can specify that. One is you just tell the submission client, hey, this is actually the Kerberos key type I want to use. Then the submission client will do the authentication for you and will generate a secret that carries the delegation token. So then mount that into the pods. The second way is you can just use an existing, if you already have a secret that carries your delegation token, you can just mount that into the pods. So when it comes to Hadoop configuration, again, there's two ways. The first is you just set the environment variable Hadoop conf there to your local Hadoop configuration directory. So the submission client will basically check the Hadoop config in that directory and generates a config map and mount that into your pods. Well, or you can also use your existing config map that you already have some, for example, some Hadoop configuration in it. So additionally to these, the native Kubernetes integration in Spark, we also work on and create this Kubernetes operator for Spark. So this is so following the recent trend of doing extensions through CRD and custom controller. So this is a so it actually has two CRD types, one for one-shot application and the other for cron type applications. And there's a custom controller that basically runs Spark Summit for you. And once the application starts running, it will start monitoring these applications. So it comes with one good thing about this is actually supports pod customization, all kinds of pod customizations through a mutating admission webhook. That means actually it can support things that are not even supported by the native integration itself. So it also comes with native cron support for running schedule applications. So it also does automatic setup for exporting your application level and driver executor metrics to a Prometheus. And also it supports installation with Helm. And the other thing that comes with it is a command line tool called Spark Control. So you can actually use that to stage your local dependency. For example, if you have some files on your local machine or jars on your local machine, if you use Spark Control, it automatically stages these dependencies onto a remote location you specify. For example, you can actually automatically upload these dependencies to an S3 bucket. Then you the Spark Control command line tool also automatically changes your dependency from your local ones to the ones on the remote location. So you don't need to handle all these things manually. So all these are taken care of for you. Yeah, so this is one of the example, so you can get a sense on how a CR or customer resource for a Spark application looks like. So you can basically specify how the driver looks like, how the executor looks like, and also you can enable monitoring or integration with Prometheus, things like that. Okay, so talking about roadmaps, this is what you would expect from the community, moving forward, that you probably will see in Spark 3.0 and later. So one thing is to solve the problem of, all the pod customizations you just saw are done through new Spark config options. But the problem is because there's so many different things you can customize with Spark pod, with Kubernetes pods. Well, so if we keep doing that, we'll end up with so many different new options. That's not something we want to do because we have to maintain these Spark conf options moving forward. So we decided to adopt a new approach. So we basically allow users to specify a pod template for both the driver and executor pods. That you can do what kind of customization or configuration you want. So for example, you can actually specify pod affinity or anti-affinity, or you can use tolerations or other things like security context. So then you just give the submission client these templates. So the submission client will use these templates to create the final driver and executor pod spec. Another thing which is often requested is the support for dynamic resource allocation. That means actually we support changing the number of executor based on the load of the application at runtime. So this actually requires a new shuffle service that can work natively with Kubernetes. We actually did this in our fork, but the way it was designed has some problems, so we decided to not upstream that into the main Spark repo. So we are currently working on a new shuffle design that will feature something we call disaggregated storage. That means actually you separate storage out from your compute. So we also want to work on better support for local dependency, like what I just mentioned. So we currently only support 2 ways for using dependency. One is you bake them into your custom images, or you upload them to whatever remote storage you want to use. So another thing is we want to investigate better scheduling support. One of the issue with the way the Kubernetes schedule works is you might have the resource to just run the driver pod, but you don't have resource to run any of the executor pods. So in that case, your application basically haunts because the driver pod is not doing, it won't do anything. It will stay there until there's resource to run at least one executor pod to run your tasks. So because otherwise the driver pod will just stay there forever. So this is something we want to work on. Well, this is particularly an issue for small cluster, like you have a cluster with only 3 or 5 nodes, you have very limited amount of resources. In that case, if the driver is started but there's no resource for any of the executor pods, then you're in a very bad position. So if you want to get involved, there's actually a couple ways. So the code is under the directory resource manager / Kubernetes under the Spark code repo. So the documentations, you can actually find the Kubernetes specific documentations on the official Spark doc site. So we also have the Spark user and dev mailing list. You can actually post questions or feature requests too. For things like if you run into any of the issues or you want to have a new feature, you can actually go to create Jira tickets. So we will frequently check and take care of. So we also have a Slack channel for Seek Big Data that we actually do a bi-weekly meeting to talk about all different kind of big data workloads on Kubernetes, like Spark or Flink or other HDFS, for example. Okay, so that's all about my presentation. So any questions?
Sorry, just a quick question. Because before, at least I will be taught is basically Hadoop, when they trying to distribute the workload, they will distribute the workload to the closest the data where the data resides. But so far, if you have an interface between that, when you assign the pod, will you also inherit that kind of capability?
Okay. So yeah, that's a very good question. Actually, so we did this in the fork. But again, so we thought the design wasn't really very good. So when we upstreamed the work into the Spark main repo, we decided to not upstream that part. We actually had that support, data locality support in the fork, but it's not in the Spark main repo yet. So that still needs to be worked on. Yeah. So right now, if you access, for example, if you have a HDFS cluster deployed on Kubernetes, and you access that from a Spark job, you pretty much won't get any data locality. Yeah.
I have a quick question on the mapping between Spark resources. For example, the mapping between node to pod to executors. And do you have any suggestions from your experience?
So are you talking about mapping from pods to nodes or? I see, got it. So the question is about like when you want to like so placement of these driver or executor pods onto nodes, given the limited amount of resources on the node, right? So that's all. So one of the reasons, like the main reason why we wanted to. So we actually in Spark 2.3. We didn't allow fractional CPU values for the executor pods. So you have to use minimally one CPU for your executor pod. Then we discover like so for small clusters, there might not even be resources to run any of the executor pods. So then we actually added support for using fractional values for CPU requests and limits. So you can like maybe bin packing like more executor pods onto the same node. This was super helpful for small clusters. So my suggestion would be to you have to do benchmarking for your application and see, and given the limited CPU and memory request for the container, whether you achieve good enough performance. If it's not, then you have to figure out so what would be. Well, especially if you have a very limited amount of memory available, you might run into GC issues. Yeah, if you have production, especially for production jobs, so your job might spend most of the time doing GC. That's something you don't want to have, you want to avoid. So yeah, so well, for especially like what I mentioned, for small clusters, you want to benchmark your application and see what's the best resource request you want to give to your container. Yeah.
I have two questions. One is that can you explain a little bit more about in your roadmap? That is the last one is the schedule enhancement in release 3, right? So yeah, can you explain which topic, which kind of focus will be the enhancement for scheduling? Yeah, another one is that the Spark job maybe in my opinion it is mostly that is batch job. Yeah, so it may be CPU heavy CPU or heavy I/O. Yeah, so especially for I/O, that kind of thing that it will affect the other jobs, other containers running on the same node. So what kind of job have you already done till now on this project? Yeah, thank you.
So for your first question, actually we were talking to a project called KubeBatch. I don't know if you have heard of that or not. It's actually a project under Kubernetes SIG scheduling. So the goal of that is actually to support Gantt scheduling. So so it's schedule a set of pods, or at once or none. So we talked to them, but it turns out it didn't really work for our use cases, because so what we really want is a guarantee that you can actually schedule one driver pod and at least one executor pod. So that's the minimum requirement we have. But the thing is the driver pod and executor pod, they don't start at the same time. So you can't really schedule them as a batch. So you have to start the driver pod first, and then the driver pod will create the executor pod. So yeah, I guess we'll still talk with them, see if there's any chance they can add support for this kind of use cases. I don't think this is unique to Spark. So for other some master-slave kind of workloads, there might be, so the same problem might apply to these use cases as well. So we wanted to find out a solution that can work for all these kind of use cases. So that's the first question. So the second question, I think if you want to achieve certain kind of isolation between jobs, or especially if you have, for example, you have two I/O intensive applications running at the same time, you don't want to schedule them onto the same node, because actually the I/O will become the bottleneck. So in that case, you can actually use pod affinity or anti-affinity to make sure that these jobs won't be scheduled onto the same set of nodes. So to do that, actually, the thing I just mentioned, so in Spark 3.0, we support using pod templates. you can actually specify in the pod templates your pod affinity or endpoint affinity to separate, pods from the same jobs, from different jobs out onto, two different set of nodes. Yeah. So that's if I would do that, that's the way I would go. Yeah. Any other questions? Cool. Yes. Thanks.